and go to the current slide. And I understand there may be a question or two.
Yes.
Okay?
I want to do a similar problem. Can you write it? If I tell you, if I just throw out something to you?
Okay. Oh, what is it similar to?
It's similar to number 8 on this test.
Okay.
If you do 90, it's find the weight of 100, but I would say find the weight of 90.
Okay, right.
Cubic
Number
feet
8.
of water.
All right. Find the weight of 100 cubic feet of water. Is that right?
Yes.
Okay. Now, let's see what we can find in the book.
I looked in there, but
This is chapter 12, right?
right.
Okay. How about on page 340? Do you have a book?
Yes, sir.
Okay. Find the weight of 951 cubic feet of water, number 12. Is that similar enough?
On 340?
Page 340, right.
Yes, sir. That is good.
Is that similar enough?
Yes, sir.
Let me see if there's any that are... that looks good enough. Okay. So this is page 340. Let me get my pen set up. Oh, before we start this, I need to make this one announcement. Y'all know about the shooter course evaluations, and you're going to be doing them, right? One other announcement, and I don't think it really affects any of you because you're all coming from work right for this class and leaving afterwards, but my office hours as posted, and here's Haley. On Tuesday and Thursdays, they've always said on the Bessemer campus from 10:45 in the morning until about 4:30 in the afternoon. Well, for the last several Tuesdays and Thursdays, I haven't been able to stay on Bessemer campus that long because I've had to come to get evaluations done or various things, one thing or another. And that happened today, so I didn't have to come over as early. It's going to happen Thursday, and it's going to happen next Tuesday, okay? But after that, I'll be back to the regular office hours as posted on the syllabus and locator card and stuff. But I just wanted to let you know in case you were trying to locate me during those times. I'll be over there basically 10:45 until somewhere around 2, and then probably coming over here sometime between 2 and 4. Except for next Tuesday, 1 week from today, I've got to be at a hearing at 1:30, so I'm going to have to leave the Bessemer campus no later than 1 o'clock. So that will be a very different day. And after the hearing's over, I'll be either over on the West campus or over here. But after that, it's back to what's listed. All right, we're on page 340. This is Chapter 12, Review Problems. And it's which number do we decide? Number 12. Okay. This answer will not be in the back of the book, I don't think, but we will figure out whether we think it's reasonable or not. Okay. Find the weight. So what we're looking for is weight, and what's the symbol for that?
WT.
Well, you could use that, but the book usually uses F sub W. It's a force, a weight, okay, and F sub W. Okay, find the weight of 900, and this is the unknown, by the way, so that's what we're looking for, of 951 cubic feet of water. 951 cubic feet of water. Now, what's that a measure of? Say again? Oh, it's flecking off and on. I don't know why it does that. What's 951 cubic feet of water? What's that measuring? What's quantity? Cubic feet. Huh? Yeah, what does that measure? What entity? What parameter? If you measure the length of this room, that would be so many feet. If you measured the area of the floor, that would be so many square feet. If you measured the volume of the room, that's cubic feet. So this is a measure of volume, okay? Capital V standing for volume because little v is usually velocity in physics, okay? So that's all they give us. They're looking for the weight, they give you the volume. What must we have to know the cubic feet, the weight of this? What relates weight and volume? What other quantity? What other quantity relates weight and volume? Oh, it's what we were studying in this section, previous section, 12 point, whatever it was, 12.5. The density, now which density? There's two different densities. Okay, not specific gravity. We need to know, it has to do with water, but which density of water? There's two different ones. You go to the chart. You're absolutely right, it was density. So go to the table, basically on page 330, 12.2, table 12.2. Notice at the top of that, there's two different densities listed. Which one are we dealing with here?
Mass density.
Really? Look at this. What was the problem state? What is the weight of water? So that means we use the weight density. That's D sub W, just like F sub W. That's why I kept circling that stuff. Okay? And what's the formula for weight density? In terms of weight and volume. Surely we know that. Yeah. Okay. You're right. For water, it's, I say you're right, I haven't found it. 62.4 in what units?
In 1,000.
I'm sorry? What units? Look at the top of that column.
Oh,
pounds per cubic feet. Okay? Pounds per cubic feet or foot. Okay? Now, what's the formula for density? If you've got that page 330 open where you found that weight density, look just across the page at 331. Very top of the page, they give the basic equations. You don't need that first one. We already know the volume. But what does the second one say?
They multiply 4.0.
Right. Okay. The formula at the top of the page. Say that again?
The force and weight of the body.
Yes. The weight density is the weight divided by volume.
Okay.
Force due to weight divided by volume. That's it exactly. Okay? And this is what we're looking for, and we know this, so plug it in, plug it in. Now, do you want to solve first for weight and then plug in, or do you want to plug in first and then solve? I don't really care too much.
Plug in, then solve.
Plug in, okay? So we'll do 62.4 pounds per cubic feet, keep up with those units, they're your friends, is equal to F sub W, that's the thing we're looking for, divided by the volume, which we know, 951 cubic feet. Now notice here, just as a precaution here, you got the cubic feet in the denominator here, you got cubic feet in the denominator here. That looks wonderful. It's just where we want them. So how do we solve for weight of the water, the force due to weight? How do you solve for FW? This is what you're looking for. How do you solve for it? Okay. Look at the problem, okay? How do you solve for that? You're looking for FW, but how is it messed up? What is it confounding it over on the right-hand side?
Force and weight.
That's what you're looking for. How do you solve for that? You want to isolate the force due to weight. Have nothing else there. What's messing it up? There's something else over there on the right-hand side. What is it? I'm sorry? Okay. Okay, not just cubic feet. 951 cubic feet. We want this by itself. We don't want anything else over here. So how do we get rid of it? How is that related? What does that line right there mean?
Divide.
Divide. And how do you undo division? Say again? Multiply, exactly. So we're going to multiply both sides of the equation because you have to do the same thing to both. Multiply this side by 951 cubic feet. Keep the units, they're your friends. Multiply this side by 951 cubic feet. Okay? Now, over here, everything goes out except force due to weight, and that's exactly what we want isolated here. So the weight of that water is, and over here, look at the units. This cubic feet cancels that cubic feet out, and now you have just simply multiply 951 times 62.5. 62.4, if I could read. Okay, is this making sense?
Yes.
Good. What do you get? I would think it's something about 60,000 or so. Say again? 59,300 what?
342.4.
42.4. Okay. What unit would that be?
Pounds.
Pounds. Perfect. Okay. Now, the only issue with this is we got way too many digits. So what do? We look up here. We have 3 digits here, 3 digits there. So the most we can get out of here is 3 digits. So start here with the 5. Count 1, 2, 3 digits. Look to the right. That's a 4. It's less than 5. So we're going to say 59,300 pounds. That's the weight of that water. That's how much water. Okay? Does that make sense?
Yes, sir.
All right. Good deal. I don't know how different the one okay, I was looking at a completely different problem. The one you have is find the weight of 100 cubic feet, which is a lot less than what we had here of water, but the property, the principles go just like that on it. Any questions? Does that answer that one?
Yes, sir.
Are there any others?
Number 5. Just can you look at
Number 5. A cylindrical piece of aluminum is 6 centimeters tall, 2 centimeters in radius. How much does it weigh? Okay. So let's see what we can find. Don't see anything in those. Well, the closest I can find on it right now, and I may not have the best, okay. It's not quite the same, but I think it's somewhat similar. Let me go back and see the problem one more time because I've almost forgotten what it was. Number 5?
Yes, sir.
It says it way. Okay. What I'm going to do instead of working that problem is talk about, it said on there a cylinder, right? Okay, and I'll point you to the back inside cover of the book.
Yes, sir.
Did you go there?
Yes, sir.
You did. And you see that in the bottom half, geometric solids,
Yes, sir.
the second one down says a cylinder. The volume of that cylinder is pi times r squared. That's going to be the area of the base, pi r squared, that's the area of a circle, times h, that's the height. And in your problem, they gave the radius, the r, as 2 centimeters, and the height, h, as 6 centimeters. So basically use that formula. Now the other thing you've got to do, though, because it says find the, I've already lost it again, how much does it weigh? Okay, now, when you're dealing with centimeters, okay, when you're dealing with centimeters, you're in the metric system. And in the metric center, they deal with mass density. So in that problem, once you calculate the volume by that formula on the back inside cover, well, before you do that, if you look at the mass density, you see it's in kilograms per cubic meter, okay, not centimeters. So what you've got to do is convert those centimeters to meters first, then use the formula for volume. Is that making sense? Okay, and that's what you got the volume, then, and didn't they say what kind of material it was? Was it lead or what? Piece of aluminum, okay? How much does it weigh? So what you're going to do is use the mass density of aluminum, which is right there at the top, and that'll give you the mass once you use that mass density formula, and then you've got to use the acceleration due to gravity to get your weight. That weight will be in newtons. It should be in newtons. Let me see if it is. Number 5, yeah. It should wind up in newtons because weight is measured in newtons, not in kilograms. So that one has several steps. Conversion, calculate the volume, use the density formula, but you have to use the mass density formula to get the mass, and then use the mass to get the weight using the weight formula. Is that all right? Make sense? Okay. All right. Any others? Okay. Because I can't find one just like it, and the closest I found was the example 2 on page 331. We already did that, but that's looking for density, not looking for weight. So that was enough different. I thought it probably wouldn't be helpful. But that's how it goes. Any other questions?
Except for the ones that you told us to work out.
Yeah.
I want to look at number 2.
Number what?
Number 2.
On page 435?
Yes, sir.
Number 2. Okay. Good question. All of them are good questions. Can I erase this ink on the slide?
Yes, sir.
Okay. This is page 435. This is problem set 16.2. Number 2, right?
Yes.
All right. It wasn't one that was assigned, but it's perfectly fine to do. Find the frequency. So what's the symbol for frequency? What does it start with? F. Okay. Now, remember we use F also for force due to friction, a little F for that. This is obviously not the same little F, so don't get them confused, okay? So this is what we're looking for, the frequency of a wave whose period, what symbol do we use for period? Anyone remember? T, you're absolutely right. And that's a capital T though. The period, capital T, is 0.550 seconds. Now, just a little bit of a hint here. Notice that first 0 before the decimal, that doesn't mean anything. It's just holding a place there. But the 0 at the end is significant. So we got 3 significant digits there, 550. Okay? Now, they say of a wave whose period is that. Okay, the frequency of a wave. Now, it seems like they're missing something, doesn't it? Okay? Except that this section, if you turn back one page, is entitled electromagnetic waves. So that's the wave they're talking about, an electromagnetic wave. And if you turn back that one page, you'll also see the formula you need, or close to it. Okay? Do they want to see the formula I'm talking about? Back on page 433.
Oh, you're talking about speed of light?
Yes, C is equal to?
Speed of light.
It is the speed of light. What is that equal to? The formula.
What is that sign?
That's a lambda. Lambda F. And we're looking for the frequency, so there that is. The trouble is, there's no T in that formula. So we might need to go back another page or two. Okay? And if you happen to see the formula on the page 428, what do you see there?
Top.
Yep.
You got the frequency equals 1 over period.
1 over T. Look at there. We don't need that formula there. That one we need. All we have to do is reciprocate the T. In other words, put 1 over 0.550 seconds. Punch that in on your calculator. It doesn't matter if we're dealing with electromagnetic waves or what kind of waves. If we know the period, we know the frequency. What would that be? should be something about 0.4 maybe. No, I'm sorry, 4 point something. Wait, no. 1 point something. 1 point something. 1.8, 1.9. What you get?
0.55.
Nah, not if you do 1 divided by 0.55, you don't get 0.55. Ah, that sounds good. How much? 1.8? Is that all you get?
No, sir.
What next?
1.81818.
Okay, 1.8181818. So those are repeating themselves. Okay? Okay. Well, we have 3 significant digits there. So look at here. 1, 2, 3 digits. Look to the right. That's an 8. That's greater than 5. So we're going to round this to 1.82. And the units are per second, or 1/2. But that also, it did when it's coming back. Or it could also be written as 1.82. What unit is a per second? Turn back one more page to page 426. At the bottom of that page, they tell you named after good old Heinrich. What unit? Bottom of page 426. Say again?
Is it
HZ, hertz. That's a 1/2. This is the same as 1/2. That is a hertz. So 1.82 hertz. Okay. Now, oops. Turned too far. I don't think that answer's in the back of the book, is it? So we can't go check it, but I'll vouch for it. That is the answer. What is the frequency of a wave whose period is that? 1.82 hertz. Now that doesn't have to be electromagnetism, so I was wrong by saying that, but if it were electromagnetism, they don't have anything on here that small. The smallest they have is 10 to the 4th. So this is probably some other type of wave. 1.82 hertz. Water wave, whatever.
I was just looking at most of the evens.
Right.
Problems.
Okay, well the odds have the answers in the back and you can check those. And that way you know if you got them right or not. That's why I assigned the odds. But yeah, evens are fine too. I'll be glad to work those anytime. Any others?
Number 4.
Number 4. Same page?
Yes, sir.
Okay. I'm not going to write the page down again, but I'll erase this. Is that all right?
Yes, sir.
Okay, number 4. 4 is a two-parter. The first part says, what is the frequency of a light wave? So though you know that's electromagnetism, so what we're looking for is the frequency. That's the unknown here. Of a light wave with a wavelength of, what's the symbol for wavelength? What's the symbol for wavelength? You were just asking me about it a few minutes ago. If you turn back one page under electromagnetic waves, 16.2, bottom of page 433, lambda. Okay, so the lambda, they've just told us the wavelength of 5.00 times 10 to the -7th meters. Okay? And a velocity, that's a little v, velocity, 3.00, sorry, times 10 to the 8th meters per second. Now, they were very kind to you there, weren't they?
Yes, sir.
They told you the velocity. But since they had already said a light wave, you could have turned back to page 433 and seen that the speed of light, the v or c, is 3.00 times 10 to the 8th meters per second. So they didn't have to tell us, but they did. Thank you very much. Okay? So, can you find the frequency knowing those two things? Flip back to that one page we were just talking about. And they put the formula in terms of C, but you could write it in terms of V because just above the formula you have V is equal to C. So what does that tell you?
If I multiply it,
Okay, but what's the formula? Always decide what your formula is. On page 433, it's listed there. In the green boxes, the formulas are usually in green boxes. C is equal to lambda times F. When they write them next to each other, that means that. But what is C? C is the same as V. It's the velocity, the speed of light. Okay? So here we have a formula with velocity, we know. Lambda, we know. We're looking for frequency. So that shouldn't be a big problem. How would we solve for frequency? How would we solve for frequency? Anybody? Anybody? Okay. Well, how are lambda and frequency related to each other? When you write them next to each other, what does that indicate? What operation?
I keep saying multiplication.
It is multiplication. For it to be addition, you have to have a plus sign. For it to be subtraction, you have to have a minus sign. For it to be a division, you have to have that horizontal line. If you don't see anything at all, they're written next to each other, that means multiplication. So how do we undo multiplication? What's that? How do you undo multiplication? Anybody? Divide. So let's divide both sides of that equation. I don't know where, okay. Divide both sides of the equation by lambda so we can isolate the frequency. That's what we're looking for. Okay. Now the lambdas go out and we have, I'm going to turn it around, frequency is equal to velocity over wavelength. And we know the velocity, it's 3.00 times 10 to the 8th meters per second divided by the lambda, which they gave us, is 5.00 times 10 to the minus 7, if I can read my writing. Was that it? I can't read my writing. Number 4. Minus 7. That's minus 7. And that unit was meters. Okay? Now, you can do this on your calculators, or I can show you how to do it without a calculator. It's up to you. You want to do it on your calculator? Or you want me to show you how to do it without one? Okay? Now, I can't divide 5 into 3. So I'm going to move the decimal one place on that 3 to the right and make it a 30. But if I made that number bigger, I have to make the exponent smaller. So that's going to be a 7. I moved it one place, so I dropped the exponent by 1. Okay? Now, I know that 5 will go into 30 exactly 6.00 times. but we still got to deal with our exponents, don't we? Okay? I know it's going to be times a 10. Now, 10 what? Okay, now when we're dealing with exponents, this is a rule. I don't know if you've run into it before, or maybe it's been a while. When you're dividing numbers, you just divide them, like 5 into 30. Okay? When you're dividing exponents of the same base, subtract the exponents. So that'll be a 7 minus a minus 7. Well, minus a minus is plus, and 7 plus 7 is 14. So that would be 6.00 times 10 to the 14. And notice here the units. The meters cancel out, leaving you 1 over seconds. And what in the world is a per second? You just answered it a short time ago. Named after Heinrich. Hertz. Okay. That would be, and frequencies are measured in hertz. Very good answer. Now, if we go back to our table, in fact, on just the opposite page there, and you see 10 to the 14th hertz, and that's the same as cycles per second. That's right at the end of the infrared band, just before you get to visible light. So it's just a little bit short of red light. It would be infrared heat radiation. All right, and that answer won't be in the back of the book either. Okay? Now that was the A part. The B part. Find the period of the wave. So this time we're looking for what? We're looking for what? It says find it. What are we looking for? You've lost it. What does it say find? Period. And what's the symbol for period?
T.
Capital T. Okay. And what was the formula for period? This one you had to turn back several pages.
1 over T.
Well, no. T can't be 1 over T. 1 over... Okay. The one we had before was frequency is equal to 1 over T. So if we wanted to flip places, 1 over F, you got it. And we just found the F, so the period will be 1 over 6.00 times 10 to the 14th per second. I'm going to go back to per seconds here. Okay? Now, again, do you want me to show you how to do it without a calculator, or you want to just do it with your calculator? Without. Okay? I can't divide 6 into 1. But I could make this 1.0, okay, and move that decimal one place to the left, and I can do 6 into 10. But if I moved it to the right, that means I made the number larger. I need to make my exponent smaller. So that'll be to the -1. Okay? And that's just a number. It's not got a unit with it. Excuse me. 1 is the same as 10 times 1 over 10, right? Okay, so that's what that is. So now I can divide 6 into 10. Well, 6 will go into 10 one time with 4 left over. 6 will go into 46 times, and 6 will go, and 6 times 6 is 36, and you have 4 left over, so it's 6, 6, 6, 6, 6, 6. 6 just keeps repeating itself. Now, that's way too many 6s, isn't it? Okay? Now, let's check out our units here. 1, there's no unit here. 1 over second is the same as second, which is a great measurement for period. Okay? Oh, I forgot. I haven't done my units yet. I mean, my scientific notation yet. I jumped the gun. Sorry about that. Let's first take care of our significant digits. How many do we have here? 3 significant digits. So how many do we want here? 3. Count off. 1, 2, 3. Look to the right. That's a 6. It's greater than 5. So we're going to up that second 6 to make it a 7. 1.67. Now we need to do our scientific notation. Okay? And remember what the rule was? When you're dividing numbers, divide the number in the number. But when you're dividing exponents of the same base, 10, subtract the exponents. So negative 1 minus 14 would be negative 15. And that will be in 1 over seconds, so that would be seconds. 1.67 times 10 to the minus 15, negative 15.
You said minus.
Okay? A negative 1 minus 14.
Oh.
So yeah, and that gives you minus 15. Okay? Now, if you look at that table, I've already lost my page again. The bottom of page 434, that table again, when they're talking about, no, they don't have periods on here. They just have wavelength and frequency, so they don't have periods. So there's nothing really to look at. Sorry. All right. That's for A and B. Any others? Okay. Any others? Haley? Okay. All right. Then let's pick up where we were last time with 16.3 sound waves. Okay. We're just getting ready to start example 1. Okay. And before we start example 1, let's go back and rewrite those formulas that we had just above it. Is it all right for me to erase what's on the screen?
Yes.
Okay. So what are those formulas? We're talking about the speed of sound in air. It's equal to, in the metric system, 331 meters per second. That's how I knew it was metric system. Plus, okay, that's at 0 degrees Celsius. Then you do 0.61 meters per second per degree Celsius. Multiply that times your temperature in Celsius, T in Celsius. Okay? Or if you have the velocity in feet per second, then you use 1087. And you don't have to memorize these. Look them up. That would be in feet per second. Right there they are. Okay. Plus 1.1 feet per second per degree Fahrenheit. But you've got a little bit more of a problem to do because you have to subtract your temperature in Fahrenheit, subtract from that 32 degrees Fahrenheit. Because this one, the first one, is measured in how many degrees above freezing. Because that's the temperature, 331 meters per second, is the speed of sound at the freezing point, 0 degrees. Well, this 1087 is the speed of sound in dry air at freezing point. So if you're needing to, per degree Fahrenheit, you need to know how many degrees above freezing. Well, freezing in Fahrenheit is at 32, so you have to subtract off 32 to tell you how many degrees above freezing. And that gives it to you. Okay? Yeah. All right. So there's our formula. Let's do example 1. Our formulas, we have 2 of them. It says find the speed of sound in dry air at 1 atmosphere of pressure. So we're looking for velocity. This is your unknown. In dry air, and that's what we're dealing with. These formulas are in dry air at 1 atmosphere of pressure. And that's what these are measured at 1 atmosphere of pressure. Okay? If the temperature is 23 23 degrees Celsius. At 23 degrees Celsius. Okay. Now, which of these formulas, oh, and by the way, now this is really sad. I'm sorry about this, but it's what they do. They also use capital T for temperature. So they use capital T for period. They use capital T for temperature. You have to tell by context. If it's got a degree symbol after it, that's temperature. If it doesn't have and has a unit of time after it, that's period. Sorry about that. They use the same letters for several things. So which one of these formulas you think we'll use if we know the temperature? And since this is in degrees Celsius, I'm going to put T sub C. The book does it. They just put capital T. That's the other way you can tell if it's temperature. If it has a C or an F after it, you know it's got to be temperature. Okay? So which formula do you use? The first one or the second one? First one, of course. So that V is going to be 331 meters per second. That would be the speed of sound in dry air at 1 atmosphere of pressure at 0 degrees Celsius. So what we've got to add to it is your multiplier, which is 0.61 meters per second per degree Celsius, and multiply that by our temperature in Celsius, which is 23 degrees Celsius. That's how far you up above freezing. Okay. Now, by the way, what is 23 degrees Celsius? Does that sound warm or cold? What you think? 23 degrees Celsius. Sound warm or sound cold? Cold. Sounds cold, but it ain't. Okay? Is that box right above your head there got a reading on it?
Yes, sir.
What does it read?
No, yes, it do. It said 92.0 Fahrenheit. Yeah.
Oh. Oh, there it is. It's coming. 90. That's outdoor temperature. Room temperature is 75.5 degrees Fahrenheit. Okay? So let me just give you a hint. 23 degrees Celsius, not far from that. Very close to room temperature. Okay? It may actually be right around 75. Okay? All right, you didn't need to know that. Well, by multiplying this, you notice degrees Celsius cancel out. Units are your friends, so don't ignore them. So what you do here is 331 meters per second plus multiply 0.61 times 23. I think that's going to come up pretty close to 15, isn't it? 0.61 times 23. Anyone do it? 0.61 times 23. Anyone got it? 14.0773, and that would be meters per second because degrees Celsius canceled out. Well, you got too many digits there, don't you? We only need 2, so I'm going to wipe out the whole there because you count off 2 digits because that has 2 digits, that has 2 digits. 1, 2, look to the right, it's a 0, we'll throw it away. Okay? So it's 331 meters per second plus 14 meters per second. That's 345 meters per second. So that's going to be the speed of sound in dry air near room temperature. So that's about what the speed of sound is in this room while we're sitting here. Now 345 meters per second, that's going to be about 3.5 football fields in a second. I don't think it's going to take many seconds for it to get from my mouth to your ears because it goes that far in a second. Okay. How did they do in the book? 345 meters per second. Good for them. Okay? Make sense? Yay or nay? Okay. All right, to clear the screen. All right, I'm not going to clear the screen. I'm glad I stopped and read the problem before I cleared the screen. In example 2, it says, what is the time required for the sound from an explosion to reach an observer 1,900 meters away for the conditions in example 1? So we're at dry air, 1 atmosphere of pressure, 23 degrees Celsius. We just found the velocity there. Here's what it is. The speed of sound is 345 meters per second. Okay? Now, what did they say? To reach an observer that is 1,900 meters away. So that's the distance. Now, this book calls distance S. I would tend to call it D, but they call it S. S is 1,900 with a bar over that last zero, meaning 4 significant digits, meters away. Now, how far is that? That's almost 2 kilometers away. And 2 kilometers is more than a mile. So you're more than a mile away. How long is it going to take that sound to reach your ear? So what we're looking for, what answers the question, the question is, what is the time? Well, time is little t. That's the unknown here. Now, do you remember from way back when we had distance, velocity, and time, distance, speed, and time, a formula we used back then? By the way, units are your friends. Let's just look at that unit for velocity. Velocity, which is in meters per second, that looks like it's got to be distance, which is in meters, divided by time, which is in seconds. Units are your friends, okay? They're not the light bulb's friend, but they're the friends. And that tells you exactly what formula you use. Distance divided by time, right? Well, we want to know time, so how do we get time out of that? What's wrong with it? It's down there in that denominator. I don't want it in the denominator. I want it up in the numerator. So how can I get it up in the numerator? Because I need to isolate it by itself. What would you do? Multiply both the sides of the equation by time. Okay? And here the time goes out, and that leaves you S is equal to velocity. I'm going to rearrange them. S is equal to velocity times time. Okay? Well, I want time by itself. So what am I going to do? What will I do? You're trying to get time by itself. What does it mean? Divide by what?
Divide by time.
No, we want time by itself. Divide by velocity, exactly. Now the velocity goes away. So let me change them around again and do time is equal to distance over velocity. So plug that in. What was our distance? 1,900 meters divided by velocity of 345. I can't write. Meters per second. Now look at the units. They're your friends. The meters cancel out, and you have 1 over 1 over second, which will be so many seconds. So pull out your handy dandy calculators, divide 1,900 by 345. And that will be something a little bit less than 6, won't it? 5 point something? 5.51 seconds. Now let's see. That looks like the right number of significant digits. Let's see how the book did. Look at that. 5.51 seconds. 5.51 seconds. Very good. Okay. Now, let's go. All right, for me to erase this slide. Okay, everybody got it? What I'm going to do is get out of this one. Okay, so I'm going to hit escape. I'm going to discard this and go to my other slide, and that is where we're picking up now. From current slides, what we have are some speeds of various media, speeds of sound in various media. Okay, aluminum, which is a fairly soft, low-density metal. Look, that's a pretty fast speed of sound. 6,420 meters per second. That would be better than 6 kilometers, almost 6.5 kilometers per second. That would be better than 2 miles an hour, okay, or 21,100 feet per second. Brass, which is I don't know, I would think a denser metal, but it's a slower speed. That's interesting. Steel, which is denser than brass, I think, but not as dense as aluminum, but it doesn't matter. It's almost the same speed. Granite, surprisingly, a rock, has a pretty fast speed. Alcohol, a liquid, ooh, it slows down big time. Water, we haven't talked about it as far as speed of sound, but water is a little faster than alcohol, but not nearly as fast as the solids. And air, dry air at 0 degrees is that good old 331. We had that before. And before they were calling it 1,089. Now they're calling it 1,090. 1,087 is what we used before. Now they're using 1,090. They rounded to 3 digits. Okay. See, all those others had 3 digits, so they rounded to 3. A vacuum, sound does not travel in a vacuum. Okay? Not at all. So you can't hear through a vacuum. Okay. Now, let's see what the next slide is. You don't need to memorize those or anything. Just know where to look them up. Okay. We've got quite a bit of distance to go before we'll need that. So let's go back. It's okay to go back to our other slide. One we'll write on. Okay. Gonna have to get my pen back. There we go. And how are we doing? I swear I can't keep up with anything. Somewhere here I think I have a watch. Oh my goodness, we're almost out of time. All right. So let's get done what we can. Beginning on page 438, they go through a number of characteristics or properties of sound. Okay? And I will list some of them just like we did properties of other things, just so you'll get an idea of what these characteristics, sometimes called properties, are. Okay? We'll start with intensity. I'm not sure you'll be needing this, but just in case the words come up, you should know what they mean. The energy transferred by sound per unit time through a unit area. Make sure I'm on the right thing. Through a unit area Okay? Thus, it's power over area. Okay. Okay. Because energy per unit time is power, and power per unit area. So the units would be watts per square meter. Power is in watts, area in square meters. Watts per square meter. Okay? Oh, we're coming up on this table much sooner than I thought. Okay? The second of these characteristics is loudness. My wife says I'm really this. Because I'm hard of hearing, I'm loud. I turn radios and televisions up loud. Okay. It refers to the strength of the sensation of sound heard by an observer. Strength. I don't know if I spelled it right. GTH. Okay. The strength of the sensation of sound heard by an observer. Yeah. Okay, power per unit area. Okay, area like here. Let me see if I can write it a little better. My screen keeps flopping on me while I'm writing, so it makes it really difficult. A-R-E-A. And area is measured in square meters. Okay? Loudness is the strength of the sensation of sound heard by the observer. Describes how strong or how faint the sensation of sound seems. Okay? Now, when you think of sound, one of the pioneers of sound was a guy named, and you know his last name, Alexander Graham Bell. Okay? And they actually named the unit of sound a B-E-L, Bell, and they call them decibels. So you probably have heard that. And I wouldn't be at all surprised if in your field you're going to be dealing with so many decibels. We usually pronounce it decibels, not decibels, but decibels. Okay? So get used to hearing that. Okay? Named after, and the unit for decibel is dB. Little d, deci, capital B, because it was named after somebody, Bell, decibel. D-E-C-I-B-E-L, decibel. Okay, actually named after him. Now, before we move on, let me give one more definition here, and that's it just below the table, pitch. I'm not talking about throwing a ball, okay? Pitch of a sound is the effect of the frequency of sound waves on the ear. The effect of the sound waves, actually it's the frequency of the sound waves on the ear. Okay? Now, you may have heard people talk about someone who's a very good singer as having perfect pitch, meaning their sound comes across to the ear absolutely perfectly. I don't have perfect pitch. Okay? If I'm trying to replicate some sound up here, what comes out of my mouth is nowhere close to what I thought I heard coming in. I have terrible pitch. Okay? But I just wanted to get that definition before we did any further. So, let me go back. Can I erase this already? Okay. Let's go back to the previous slide. I said we wouldn't get there soon, but we got there sooner than I thought. To this slide. And this is just a little bit of the sound level in decibels, which relates to intensity, the threshold of hearing, this is for you normal people, would be down there about 0 decibels. Okay? Now, for me, it's probably going to be 10 or 15 or 20 or 30 or 50 because my hearing's so bad. Okay? Now, let me say a little bit about decibels. Okay? Notice when you go up 1 order of magnitude in intensity, from 10 to the minus 11 to 10 to the minus 10, or 10 to the minus 12 to 10 to the minus 11, you got 10 units of decibels. So it's 10 times the logarithm. And that's the negative logarithm. We won't get into that. But that's what the decibel is. Okay? So a ticking watch, I don't know the last time I heard one, but that was around 20 decibels. Okay? That's very, very, well, it's still very, scarcely audible. I wouldn't hear it. Whisper, that's around 30 decibels. Leaves rustling outside or a refrigerator running, as long as the compressor's in pretty good shape, that's about 40 decibels. Your average home or street noise is around 50 decibels. That is unless you have teenagers. No, I didn't say that, did I? I'm sorry. Okay. All right. The normal conversation or the sound made by a microwave oven, that's around 60 decibels. Okay. A car, alarm clock in city traffic, that's around 70 decibels. Okay. There are some mornings I don't even hear the alarm clock. My wife will say, "The alarm's going off," and she'll sometimes have to say it several times before I hear it. Okay. Now, part of that is because I'm a really sound sleeper with the other part. So a car, alarm clock, city traffic's around 70 decibels. Your garbage disposal, vacuum cleaner, outboard motor, noisy restaurant, that's around 80 decibels. A factory, typical factory floors, electric shaver, screaming child, that's around 85 decibels. You've never heard of any of those, have you? Okay. A lawnmower, passing motorcycle, convertible ride on the freeway, that's around 90 decibels. Okay. You're beginning to get up in the loud to very loud range here. Okay. A hairdryer, a diesel truck, a chainsaw, a helicopter, subway train, those are around 100 decibels. Okay. Car horn, snowblower. Yeah, when's the last time you operated a snowblower? That's around 110 decibels. A rock concert or a propeller plane, 120 decibels. Now you're getting into the deafening and painful range. And 100 feet from a jet engine or an air raid siren, that's around 130 decibels. A shotgun blast, especially if it's somewhere fairly close to you, 140 decibels. If you're practicing firing a firearm, wear sound suppressors, okay? You don't want to have lots of those noises. You'll damage your ear. When they say deafening, that means it causes deafness, okay? And that's way up at the car horn snowblower. You don't want to be around that too long. Rock concerts, that's getting to the painful region, okay? And then anything beyond that, jet engines, air raid sirens, shotgun blasts, you're doing some damage, okay? So those are the typical, not typical, but range of sound levels. But if you look at this, isn't the human ear absolutely fascinating? It's going from 100 down to 0.0000000000 watts per meter. One. I'll put a 1 in there. That's an incredible range of sound, and your ear can pick it up. It's doing damage up here, barely hear it down there, but that's an enormous range of sound. We've got amazing bodies, okay? Now, how are we doing on time? We're out of time, aren't we? We'll begin next time with the human ear. The slide here is just before the Doppler effect. We won't do much on this. You probably have dealt with it before in biology class, but we'll just show the slide and go on. But that's where we'll begin next time. Any questions?